Okay, welcome back everyone to the second installment of Stevo's lectures.
Okay, so let us go back so that I'm repeating the basis problem. Is, basically, you like to find a basis that is reasonable. And the reasonable typically means that it's finite. Sometimes you'll have a problem there, a solution to the problems where they're actually countable, enumerable. And this is, as I said, more interesting, which we are going to concentrate on the first part of today's lecture. And this is the typical problems that have been solved. The last one was still unsolved. So I like this last one because there's word metrizable there. Because some sort of we have another way to view metrization problems, some sort of problems of this sort up. So in other words, you like to find some finite many structures or spaces that are responsible for non-metrizability. Okay, linear ordering, that's the easiest and most famous, although from the, in other words, from the point of view of a theory, it's a very well developed theory and it's very old. So let's start with that. That's very immediate. This is actually immediate consequence of Ramsey's theorem, right? That every infinite linear ordered set contains one of these. And you have this corollary that was of that sort, which I mentioned you. And you have this other one. Can you do the same thing with the countable? Can you characterize the same way countable linear orderings, which is exact equivalent to this other version of the problem. Okay, and now there's that very well-known story, which I would like to go over it. I think it's a good story to know. Well, quasi-ordered, it's unclear who first came to it, although later it becomes one way to say classify structures. And there are various parts of mathematics where they are proving a result that this class of structures is well quasi-ordered, especially the finite, in the class of finite structures. And this is the well-known conjecture that is due to Fraise, where the class of countable linear orderings is well quasi-ordered. He might have known about the problems about the uncountable linear orderings at the time where he asked it, but maybe there was another reason why he asked it. And there is a very well-known theorem that has answered this in the most general form. Sigma scattering, of course, gives you countable, though it actually countable doesn't need sigma scattering, you need a just scattering, right? Because the rationals are on the top, so this is not going to influence a countable linear ordering or not being well quasi-ordered. But the title of this slide say from well to better. You see, suddenly there's a change. Fraise asks for something and you get another answer. He wants to say, well, it's not just well, it's better. And it's not, and Rich Laver is not a person who likes to state results in the most general form. And actually, this is necessary. In other words, there was no other way. There was no other way of proving. And that was, anyway, this is that corollary that every reasonable subclass of sigma scattering has a finite basis. So there's a story behind, and it's related to the Ramsey basis problem. That's why I mentioned this. And it's due to Nash-Williams, which in some sense invented the infinite dimensional Ramsey theory and is as a part of Borel combinatorics. This is his key definition. Collection of a finite set is barrier if every infinite set has an initial segment in it, and no two elements are comparable inclusion. So very much present and kind of a thin. And these are examples, not surprisingly, the one that Ramsey was dealing with. And there's another one which shows that actually even much earlier in 30s in the geometry balance spaces by Scher. This is a well-known Scher barrier. This has an infinite rank. Rank is, you can think about it in the Cantor-Bennigsen rank or some sort. There's a natural ranking. So barriers are in some sense versions of ordinals. Although for a given rank, you might have many. And this is that invention of the infinite dimensional Ramsey theory, or even one of the first results in Borel combinatorics. So barriers are Ramsey. If you split it into finally many pieces, one restriction, this restriction is the intersection of F with the power set. It's not that you trace every element of S on it, but you look at all members of F that are subset of M. That's a result. See, you can there are various proofs of that, and all of them are rather interesting. One of the proofs could be on the rank of F. The other proof, which is actually Nash Williams' original proof, was using so-called combinatorial forcing. It's actually 2 or 3 years after forcing. In other words, this is one of those accept, reject combinatorics as the first. Okay. And this is the brilliant definition. Something really very, very much non-obvious. So you see, he doesn't like WQ, better-quasi-ordered. He wants to make them better. And this is why, how he makes them better. He said for every function from a barrier into Q, there exists 2S in a special relation. This is a shift relation. Shift relation. So the order is preserved. And there is that reformulation by Simpson. It's a nice one to think back on your mind. Okay, so I just want to mention that if you take this barrier of a singletons, that if you just restrict the definition of the barrier of singletons, you get just another definition of a better-quasi-ordering. Because the shift for singleton is simply that one is on top of the other. The shift for singleton is always true. Okay, so that's Simpson reformulation, and then you have here shift, actual shift. You can think about this as increasing, and then it's actually a shift, the usual, what people call shift. Okay, so that's notion of a quasi-ordered. And this is the reason why he wanted this, because he was take this coordinate and look at all ordinal sequences of, take them all strictly increasing, and there is that very interesting relation, less than 1. 2 sequences, one of length alpha, the other of length beta, is less than the other if there is a increasing injection of the domains, so that on each coordinate you have a domination. Now, why this is somehow, when you see this result, why this is relevant to Frise conjecture? Think about the scattered ordering. There's that house of ranks. So initial assignment, you're taking the well-ordered sums of a scattered ordering of the lower rank. So you're really dealing with this ordering. So it's not actually surprising that this is relevant. Actually, it turned out to be exactly what's needed. And the reason is this. This is the reason why Nash Williams looked at it. So WQ in general doesn't have this property. So a very important example of Richard Dorado, and that's a theorem. So if Q is better-quasi-ordered, that shows any space of sequences, or any space of sequences. So now that actually you can say you don't need all ordinals to that. You need ordinals up to omega-1, but this is a special result actually due to Maurice Pouset. that you don't need this. This is actually if only, this is a characterization, by the way. Q is BQ if and only if Q to the less than omega 1 is WQ. Okay. Okay, so now we got, so that's an explanation of the behind labor result, and we have already seen that behind is one of the key fact there is indeed this Nash-Williams Ramsey theorem, which actually allows you to prove results of that sort. So, and now let us look at the separable in orderings, because countable in orderings are separable. So then you want to build on that, right? You want to see how much you can extend it, and there is a current example on the level continuum, and that's probably what might have been known to Fraise. So it's not trivial quadrat. This is a usual example, today's quite standard way to actually kill increasing map by enumerating them. And there's a curious little problem here. What is this? How far you can go with Lever's theorem in this direction? And Baumgartner say you can if you are, of course, continuing hypothesis is going to stop you at alpha 1. That's just about it. And Baumgartner was saying, well, if this is a proper forcing axiom, which is alternative to the continuing hypothesis, gives you that you can go up to the Dushling-Miller restriction. It's another reformulation of the theorem. The reason why I mention it because we are going to be looking at extension of Lever's theorem in a different contexts. Okay, so that's a separable in ordering, and also I need them for next. So in other words, once you believe that you understand separable linear orderings, then you should go to orthogonal, which is exactly this. Orthogonal is the not containing uncountable order set, nor reversible order, nor uncountable separable linear ordering. Surprisingly or not surprisingly, this is a non-empty class. That's by the name, you could guess that. It was not very much ringed in this 1935 paper, although it is there, but so Specker was rediscovering. Okay, there is that, of course, alternative as a beautiful result by a former student in Toronto with that this Baumgartner's result for a separable ordering goes towards the Anschei, towards orthogonal. So the Anschei ordering is well quasi-ordering. Actually, as a matter of fact, it's better quasi-ordering. In other words, it does uses the Nash-Williams theory, among other things, this Bell category statement, proper forcing axiom. Okay, so then there's again, you have this basis problem. Okay, so that's if you look at the basis problem for uncountable linear ordering, there's a very important piece, very influential for us because we learn lots of things from it, partially. Uncountable separable linear orders have one element basis, and then the result of Moore that Anschei orderings have also a basis, finite basis, a matter of two-element basis where C is any uncountable linear ordering whose Cartesian square is union count many chains. This is another one of these questions where such a thing exists, which was asked by a countryman, which was resolved first by Scheller. And in fact, the conclusion of this theorem was a well-known conjecture of Scheller. And if you combine, then you have a 5-element basis. It's unimportant which B and C you choose, any one of them is good enough. In other words, the equivalent under this embedding relation. equivalent meaning there is embedding from both directions. Okay, so this is that characterization of countable linear orderings that we are looking. It's a kind of a metrization problem. And now we go to the trees. See, you would think that you should first consider this, and then linear orderings. But actually, trees are a little bit more complicated. The linear orderings, well-ordering linear ordering gives you immediately a tree. In some sense, so that's how you should think. Expanding linear ordering by a well-ordering of a say minimal possible size, it gives you a tree that somehow decomposed linear orderings according to the. You can think about it as a tree of types. So usually how people think about it. And then you like to sort out the problems there. And there's the topological embedding. The first was done with this embedding, with a strong embedding, which preserved not only strict relation, but also it preserves the meets. I mean, the splitting is splitting, preserving splitting. But it's not necessarily level preserving. So the trees in this context are, we are thinking as you can think about trees as graphs, but it's better to think about the tree as a partial order set with a property that possesses a total order. And this is the very famous result that finite trees are well quasi-ordered by the relation, by the topological relation. When I was presenting this morning, I could not find a reference of a Polish topologist whose surname was Todorčević, who discovered this in the topological context, stating that the finite dendrites in the planes is WQ. So the same result, really. So in other words, this result is a natural in topology. And there is a result, the class of all trees is about quasi-ordered. That's actually why, that was the reason why Nashville developed theory of better-quasi-orderings, just to extend classical theorem. In a series of papers, early 60s, ending by 1968, so say 64 to 68 years, developing. You see all trees. And as a result of labor, it says that actually this is true of all scattered trees. Except there is a little bit of, again, a problem, because again, Rich labor would never do that. So what's wrong? All trees and then some substitute trees. Because these are graph theoretic trees. So these are trees of height omega. So these are trees of height omega. Yeah. Well, these are set theoretic trees. It can be any height. Sigma scattered means that they don't contain a copy of the complete binary tree of height omega. Scattered, that would mean sigma scattered union of. So that's another very strong result. Rich labor by using his method. Extension of he had to extend Nashvillians. Okay, so that's these initial theorems about trees. Yes? No, I on purposely wrote it like that just to make a joke. I said it would look like one theorem is the consequence, immediate consequence of the other, which isn't. Because the first theorem talks about the graph theoretic trees, the other theorem talks about set theoretic trees. So there's no way you can deduce labor from, but you can deduce Nashvillians from labor. Because every tree of height omega is sigma scattered, right? Because union of first n many levels is scattered, right? So this theorem is stronger than that. That's the reason why Ray was wanted to extend Nashvillians. Yeah. Okay. Okay, so there's that unshaped tree. For example, to the Koenig's lemma. And this is one of those trees that have occupied me a lot to classify them. See, this is the counterexample to the Koenig's lemma, which means that anything you want to extend from on a countable context to uncountable context, you're going to hit this problem. So you better know it. So you better try to classify, for example. You have to classify this. And that's a basis problem that I would like now to describe you. So what are these examples of Koenig's lemma? There is a one. And there is a first natural question: can you classify them using this topological relation? That would maybe a good would have been a good answer, except there is that this is not true. They are not, and even in the much weaker ordering, there's a just strictly increasing map. You don't need to preserve means. So that was the bad news, but actually not so. Because when I looked at how I got these counterexamples, I could these are very nice arbitrary trees, and I could in this nice arbitrary tree I could not get an interchain. Remember, WQ means there is no infinite interchain and there's no decreasing sequences. So I could not find infinite interchain in that. And that's the theory of Lipschitz trees. So what are these more important arbitrary trees? It's a metric theory of trees, I guess, which comes from the, is somehow motivated or inspired by the metric theory on ordinals by Vox, on ordinals somehow, okay. So it's a very natural. You see a tree has its level, delta xy is the level of the place where they split, and this other level. So delta is a level, not the node where they split. It's a level of the node where they split. So that's a Lipschitz. It's like a Lipschitz condition, right? Yeah. Because remember, in the ultrametric you have to reverse. So it's indeed a Lipschitz. Okay, so that's a map. And here is the definition of an irreducible arbitrary tree, which I call Lipschitz tree. There's a profusion of Lipschitz maps, self-maps, partial self-maps. In order to not to cheat on this level, you assume that the map send a node of a given level to a node of the same level, so that you're not spreading this, then you are making this Lipschitz artificial. So a level-preserving map on an uncountable subset can be made Lipschitz on a subset, uncountable subset. And they are there's a profusion. If you asked, say, these problems in 1960s and your answer trees in 1935, you will have probably difficulty answering it, or even 1970s. Yeah. But now somehow there are lots of them. Basically, any characteristic of the walk you put is Lipschitz. You don't need to worry very much. They are there. And this is the result, a global version of the result, but I'm going to explain you why this is true. In some sense, what is happening? There's a chain of Lipschitz tree, which is a discrete, meaning every Lipschitz tree has an immediate successor. So there's these convex pieces where either n chains or z chains, sometimes n, sometimes z. If you mod out by it, you get a very homogeneous ordering, meaning there is nothing there. There is actually no surprises could be hidden there. It's a generic ordering. Okay. And how this is done? You attach an invariant, which I think is interesting by itself, which is this strangely looking collection of sets U of t, set of all levels. For it is an uncountable set with a distance set inside. So this is first of all, if I was smart enough to put a pose there, you would not guess that this has anything to do with this will be a filter, right? Because this is unlikely to be filtered. It's very unnatural to expect that this will be a filter, because it's in arbitrary arbitrary trees, it's never filter. But for Lipschitz tree, these are always uniform filter. And if you assume the CC productive then is actually ultrafilter. And now there's a Ramsey there. Ultra and the CC productive, non-productiveness CC statement is a negation to a very natural Ramsey theorem for on omega 1, actually. And the most pleasant thing is the last one, that the trees are equivalent if only ultrafilters are equal. So it's an invariant of the equivalence relation of this. So this remains, there's a strict increasing map from T, S into T and vice versa. They are uniform ultrafilters. And now suddenly we have lots of Lipschitz trees and lots of uniform ultrafilters. And now we have to see what is happening. So the first one, you would like to shift them. So you assume that they are in a reasonable representation, all of them are isomorphic to such a thing, and the G shift is simply shifting this is the notion here, shifting, of course, the place where you can. The G has a partial map, so you simply push the functions up or down, depending what the G does. Typically, G is increasing map, so that you don't mess up, because otherwise you have a problem with the Lipschitz. And this is actually one very, very surprising consequence of all. There's only one tree, and there's only one ultrafilter. In other words, in the context of PFA, there's only one current example to the canonical lemma, and there's only one ultrafilter associated with it. Let's see why. Okay, so if you have a Lipschitz tree and the range of G is in U of T, then the G of T is also Lipschitz tree. So think about these G's are really Rudin-Kistler reductions. If you have a partial map, then if G is regressive, then there is no. In other words, there's somehow suddenly there's some sort of ultra power going. So if the mapping is aggressive, then there is no strict increasing map from TG inside. And if it is expanding, the other way is around. Expanding means that f of psi is bigger than, G of psi bigger than psi. And this is the set 5, this tells you there is really only one Lipschitz tree. All of them are really some simple permutation of each other. So every two Lipschitz trees are related by a map. So therefore, all these ultrafilters are the same, modulo permutation. Yeah. Okay. Now you like to see what is the tree and what is the ultrafilter, right? You like to see, because these are examples that you need to worry. And also you'll need to a little bit, you have to say a little bit what's happening with the other Armstrong trees. Maybe there's some hidden thing there that is not captured by it turns out that actually there's no. The interval is empty, so the shift is immediate success. So this chain was discrete, and there's that comparability. That's the reason why I was not able to find antichain in the Lipschitz tree, in the trees that are working. And this is every Armstrong tree is comparable with every Lipschitz tree, which means this discrete chain splits Armstrong trees into clouds, into cuts, that is in cuts of that. So in other words, they are irrelevant as far as the canonical lemma is concerned, because they admit strict increasing map to a Lipschitz tree and vice versa and others. In other words, the reason why they don't have a uncountable chain is Lipschitz trees are responsible for that. There's nothing to do with the tree themselves. And there's no strictly, and I purposely put this 2000. This is the Mittag-Leffler semester or a year, I think, I forgot, where this is appearing in the Preplit series. Paper actually appeared a few years after. And there's a very deep result of Justin Moore that actually is used in some sense. Both of these two theorems are equivalent to this theorem. So there's a Ramsey phenomena specific, which is equivalent to these two. I presented, this was the first time that actually I realized that Shelach conjecture must be true, because it has a very natural reformulation. And indeed, this was verified by Justin Moore a few years after. And so this is another Ramsey theoretic statement. We already know by Sierpinski or other that there are very strong counterexamples to the Ramsey theorem for uncountable, but see, there are no ones of that form. And I should perhaps notice that the fact that U of t is not of the filter is another, the fact that the U of t is of the filter is another statement of that sort. It's actually a specific case of that. So ultrafilter, the U of t being ultrafilter is an instance of that, except that you can prove it just from a big assumption that the countable chain condition is productive, where here you need a full machinery of proper forcing axiom. Okay, and now I'm interested in this ultrafilter, what that is. This also must be something important, right? There's only one object, so there's a one ultrafilter. Of course, on omega 1, it's difficult to analyze because we don't have a much theory of ultrafilter on omega 1, unfortunately. Maybe one day there will be. I should point out that this ultrafilter is unusual, that its definition, it is definable, is a sigma 1 definable in H aleph 2. And as you know, there is no sigma 1 definable ultrafilter in H aleph 1. Remember, this is the difference. So what I want to do is simply push this ultrafilter on omega 1 and see what happens. It's a very natural thing, right? There's always such a map. Nowhere constant meaning that is not constant on a member of the ultrafilter. So image is a non-principal filter, as a matter of fact, ultrafilter. And now you'll say, well, suddenly what are you doing? You took the canonical object and moved this with F, etc., and you get a mess, right? As a matter of fact, not. You got actually only one ultrafilter. First of all, it happened to be selective, meaning it has to happen to be a Ramsey ultrafilter. Again, you have a Ramsey there. And it's only one modulo Rudin-Kistler and doesn't depend on T nor F. So in other words, you have a definable Rudin-Kistler class of a selective ultrafilter with no parameters. And I like to point out this because selective ultrafilters are usually constructed using some cardinal characteristic of the continuum is equal to the continuum, and here you have other way around. That some cardinal characteristic of the continuum is not equal to the minima value. So it's curious. Okay, and that I just remind you what the selective is. Sometimes it's called Ramsey. It's defined in a paper by Choquet. With different names, two papers. He did it for some reason he needed them. So it's every map is constant or one-to-one. These are the two canonical equivalents, Ehrlich-Schrader equivalence relation on singletons. The Schrader canonical equivalence relation, which we are going to again remind today. These are that's why the Ramsey is behind. So somehow it witnesses this phenomena that equivalence relation has to be there are no many equivalence relations there. Okay, so now I go to the completely different setup, which again will be which I find also very interesting for various reasons, because it has versions in all parts. It has a Borel combinatorics version. There is also a combinatorial version, and also there is a very strong connection with the Ramsey expansions, and we are going to see. which is very much unobvious at the first sight. So let me just remind you what a Tukey is. So for a two partial order set typically directed, there is a map that maps unbounded sets to unbounded set. And then there's that dual form, cofinal set to cofinal set. And there's that cofinal similarity. In the case of a directed set, this is actually saying that they can be embedded as a partial order set inside the single one cofinally. This was how Tukey actually came to this. Well, this is actually his theorem, this characterization. And ultrafilters are, I want to point out the first ultrafilters. And this is the maximal type of a directed set of any size. So this is rather obvious because unboundedness is easy just to be infinite. So any one to map for any directed set inside, say even singletons of theta is Tukey. And there is that interesting example of ultrafilter on omega that really has the maximal Tukey type. And there's a very still open question where there are any other. There is a Tukey type ultrafilter that's different from a singleton and different from the maximal. This is a version of p-point problem. P-point, which definition I should have included. So these are ultrafilters that are downwards directed under all, countably directed downwards under all exclusion. In other words, you have a sequence of members of U. There is a member of U that is included modulo finite in all of them. It's easy to see that actually it cannot be maximal. So it's a variation on the p-point problem. P-point, this is the notion of Walter Rudin, quite well known. And there was that, again, classification result. You can direct a set of a particular size, you can classify. And that fact, you can classify all partial order set of that site. This somehow, so maybe this is intelligible what these things are, but if you have in mind some of the standard partial order set of sizes of one famous ones, converge chain condition or a Baumgartner poset for shooting a club through to a stationary set or some other, they are there, the types are there. So that was the one of the classification placed in our solution of this particular basis problem. And now I said I like this because somehow it has a very interesting descriptive combinatorics context, equally interesting and maybe even more interesting. And that this came from that. That, of course, this is a very old, the people were looking, actually the first person to look at this descriptive combinatorics context was Isbell, by simply getting some Borel posets saying that they have different types in the 60s or 70s. So it's, but we wanted actually to take it some more general view on that. So there's a notion of a basic. So there's a partial order set, which is actually upward directed. There's a least upper bound. There's a topology on it, which is aprobometric, which has the following two properties: that the meet, so union map join is continuous. Every bounded sequence has a converging subsequence, and dual notion. Every converging sequence has a bounded subsequence. The moment looks curious, like playing with words. But as a matter of fact, this topology is unique. You don't need you need order, except that when I fix the slides, I should say this topology is uniquely determined by the order itself in the following way. is that topology is sequential convergence, where a sequence is convergent if it is order convergence, or a lim sup equal lim imp. That is missing here, and has this property in on one of these. Every subsequent has a further subsequent which is bounded. The collection of such a sequences define your topology. This topology has to be metric if the ordering is basic, if only. So it's this is actually observed by in a conversation Fremlin when he heard this notion, because he was writing this section on the book, his books in measure theory. Okay, the examples, again, the p-point ultrafilters are basic. So in other words, the ultrafilter that Rudin was considered is basic, and there is a sigma ideal of compact sets, rather important in the context of descriptive set theory. Analytic p ideals on omega basic, and there is an analytic equal Polish phenomena there. And there's that little thing that you suddenly are saying that the basic orderings have essentially a minimal element. So there's some sort of they have a one element basis if unless they are trivial. And now the most interesting thing in all our study, I think, is this automatic definability. You have you decided to study Borel-directed sets under Tukey reduction. You have a nice category, but very bad maps. So you are really doing something wrong, or at least this is how it feels. But it's now actually not so. So for a basic order, if there is any Tukey reduction, then there is a cofinal map that is Borel. The Tukey itself is a little bit not Borel, but is so what is called socially measurable. So in other words, because you have to choose. It's some sort of a selection, uniformization actually. So the Borel is in this direction. Remember, having a Tukey map is the same as having a cofinal map. There was these two dual characterization. The niceness, Borelness comes from the. Okay, so I see the basic orders, definable ones are closed downwards. So in other words, we are in a good category. And when we tested this on the p-point, actually the map is continuous without, these 2 point. If the upper one is, then the lower one is actually, there's a continuous map which is actually a monotone with cofinal range. So therefore, p-point ultrafilter have no more than continuum many Tukey parameters, which means this class there is relatively small. Remember, the class of this top, Isbell's top, is canality 2 to the continuum. Well, this is canality continuum, if you just want to. And now you'll say, where is Ramsey there? Where is the expander? And actually there was. I remind you again what I told you yesterday, but slightly just to remind those people who were not there, that you can make arbitrary relation canonical, meaning just dependent on the ordering. The expansion is disordering. I should have put less than or equal, so the equality is there. Okay. Simply things to put. This is just to remind you, you see the equality is there. In other words, I'm doing what possible people do. You are putting equality under the rug, but actually it's important. Okay, so a canonical relation, this is what, so there's a positive solution to expansion problem. Recognizing canonical relations, of course, enumerating is very tedious. This is essentially only, I think that I have a student homework where they actually use computer to get it in dimension 3, very long list. But typically it's a very tedious problem to enumerate them. And when you do, sometimes you get interesting. And there's a one that's relevant for us now for a Tukey is this. Very well-known result, and that's why the word canonical is there, because people they got stuck with this word canonical because of this result. Every translation is of the form projection, given by projection on some set of coordinates, essentially. That's every translation on that. We know that it's actually canonical by the previous one, except that they had to do a not so trivial classification to figure out what are all these canonical, what are the ones that are important, what are the ones that are essential. Well, just let me maybe that was not so clear. See, from the Ramsey and Scholar, it tells you that if you have two n-tuples, which they are in some order, some relations, if they're equivalent, then no matter which other tuple you come with in the same configuration, they are going to be equivalent. This equivalence will not change, and similarly for non-equivalent, except that your relation is not arbitrary. There's a transitivity. So using transitivity, you can sort it out and get this beautiful result. That's actually what most of these, any of these Ramsey expansion problems have these two sides. The pure Ramsey side, which tells you there's a canonical one, and the other one you actually have to do the work to figure out. And we go back again to Nash-Williams. Not surprising. I'm just repeating you, and I'm repeating the examples. And I'm repeating the barriers of Ramsey. And now the result that we're interested in is this. So what this says is the extension of the Erdős-Schrader result to arbitrary barriers. Why is that? Because you see, Erdős-Schrader was canonizing equivalence relation on the first example, while they are trying to get on the second. Notice on the first one you had only finitely many possibilities. On the second you don't. You have infinitely many. So the basis problem have a list that is infinite, but it's recognizable. So this is one of the example where the basis is infinite, although you can specify it. Now let us see how you specify it. Well, there are a few words here which I'm going to again redo it again, but let me just tell you, internal mean that there is a map f of s subset of s, that's internal. So like in the other one, you're taking the coordinates that are important. And that the uniqueness, meaning that there are that you don't have a two or more solution, meaning that somebody else is coming and finding another invariant and completely different. No, being internal, and that the image is a barrier freezes you a translation. There's no more changes. So again, f of s subset of s, and if f of s and f of t are different, then they cannot be comparable. Yeah. So in other words, the range is a barrier. And this is the result, Tukey result. It appeared in a paper with Dilip. It have here also, and I have some other result of that sort, but this is one that is pleasant to state because it's exactly the connection that I would like to see more in the future. Okay, if you take a selective ultrafilter and you have a non-principal filter below it, then this is not only that is equivalent to T in the Tukey, but is actually Rudin-Kistler equivalent to some Fubini power. For a selective ultrafilter, taking the arbitrary Fubini power don't change its Tukey type. They're all the same, no matter how high Fubini power. And also, perhaps you're not clear what the Fubini power is. Also, it's going to be clear in a moment when you see when I give you a sketch of the proof. Remember, in any lecture there should be some sketch of the proof. Right? I thought that should be good enough because it's relatively clear. The set of the ideas behind this are perhaps not so easy to get towards. It's perhaps not so obvious. Okay, so they are minimal, non-principal. So in our selective, these Ramsey ultrafilters are essential objects in the Tukey classifications. They are minimal objects. Okay, this is how the proof goes. You take V selective, U arbitrary. By the automatic continuity, this thing with Slavic, there's actually a continuous map, achiever monotone, that maps V to a generating set of U. And you define the mapping that picks a minimal element of the image. That's a map with a countable range. It's also continuous. And now, by continuity of a map, there's the basic, you must be, because the range is discrete, you must be constant on a basic open set. And you take the minimal S with that, that's going to be barrier. So you really have a function on a barrier inside N. In other words, you have equivalent relation on barrier. You need to canonize this. So it's simply constant value. That select, okay, there's a selective version, you see. Selective ultrafilter, Ramsey ultrafilter, I think they should be called generic. They're generic, meaning that any statement or any mathematical statement says every infinite set contains an infinite subset with some property. That infinite set, if you started in ultrafilter, that are going to be also in ultrafilter. This is what the selective version is. So there is an M where the internal map, that's again reformulating the canonization result. There is internal map with this property, and there is a one-to-one, meaning that it catches the equivalence relation. One-to-one map size which commutes with this. So it gives you back F2. If you take a C range, because it's an interchain normal inclusion, but also its density, it must be barrier. That's another consequence of a slight extension of a Nash-Williams theorem due to Galvin. In other words, modular restricting on the range or a member of U, this is actually a barrier on some set. So this mapping G is a one-to-one mapping that moves our ultrafilter U to some ultrafilter that looks like this. You take this barrier C and you restrict it to arbitrary sets in V. But when you think about it a little bit, this is actually a Fubini power of V. That's actually the right definition of a Fubini power. Remember, Fubini power was this usual Fubini formula, U square, U3, etc. At the control stages, you do some arbitrary thing. And indeed, you can do arbitrary things, although this is still your Fubini power. But anyway, that's how you should be thinking. For a selective ultrafilter, because of the Ramsey of the selective, because of the selective Nash-Williams, this is an ultrafilter. So ultra is responsible, Nash-Williams is responsible that this is an ultrafilter. And this is a Fubini power, and there's a one-to-one correspondent, that's a solution. So that's, I think, a good place to stop because we have another thing going on.